In this session, we're going to explore hyperbolas. A hyperbola is a shape that looks like two parabolas back to back, and they can be oriented horizontally, that is, left to right, or they can be oriented vertically, that is, one on top of the other. A defining characteristic of hyperbolas is that the farther away you get from the center, the closer and closer you get to asymptotes. They go asymptotic towards the edges. For hyperbolas centered at the origin, we're going to see two equations. For a horizontally oriented hyperbola, that is left and right, we're going to see x squared over a squared minus y squared over b squared is equal to 1. And the way we're immediately going to be able to recognize the equation as that of a hyperbola is that the terms are separated by a minus sign. That is, the two terms have opposite signs. The other equation has x and y reversed. We have y squared over a squared minus x squared over b squared is equal to 1. We again have that minus in between the two terms, and the way we know if it opens left and right or up and down is by which variable is positive. If the x squared term is positive, then it opens left and right. If the y squared term is positive, then it opens up and down. There are, of course, characteristics of hyperbolas that you're going to be asked to identify. One of them is going to be the center. The center is the point where the asymptotes cross each other. There are also vertices. Vertices are where the curve is most prominent. Okay, so they're along the same line as the center, and it's where the bend is greatest. Those are the vertices. And then, as with the other conic sections that we've seen, there are also points that are called foci, and they are inside the curve. If you're seeing relations to parabolas, I can understand it. These aren't parabolas because of the asymptotes, but they have some of the same characteristics, that is, a vertex and a focus, or in this case, vertices and foci. A moment ago I just said that the vertices and center are on the same line. I didn't mean on the same line as metaphorically speaking. I meant literally. There's a line that connects the foci, the vertices, and the center. And in a horizontally oriented hyperbola, that would be a horizontal line. And in a vertically oriented hyperbola, that would be a vertical line. That line is called the transverse axis. And so we might refer to a horizontal transverse axis or a vertical transverse axis, and that just indicates the orientation of the hyperbola. Considering the equation x squared over a squared minus y squared over b squared equals 1, the a squared that's under the x squared gives us the distance between the center and the vertex. That is to say, the distance between the center and the vertex is the letter a, or the number a. And that's going to be to the left and to the right in the case of a horizontally oriented hyperbola. In the other equation, the y squared over a squared minus x squared over b squared equals 1, the a has the same function. It's still the distance between the center and the vertex. So we're going to take the square roots of those numbers in the denominator to find the distance between the center and the vertex. As far as the focus is concerned, the distance between the center and the focus is going to be denoted by the letter c. And that's true in both orientations, horizontally and vertically oriented hyperbolas. The distance between the center and the focus is going to be c. You may be wondering, where is c coming from? Well, it's the case that a squared plus b squared is equal to c squared, like the Pythagorean theorem. And this equation, this relationship, will give us the distance between the center and the focus. The a squared and b squared are coming from the denominators of the terms in the original equations. There are a couple of other ways we're going to use the number b. But first, let me clean this up a bit. The letter b also pops up in the equations of the asymptotes. The asymptotes are lines, and so they should have equations that look like lines. In the case of the horizontally oriented hyperbola, the asymptotes are going to be given by y equals plus and minus b over a times x. So let's explore this just a little bit. The plus and minus is because one has a positive slope and one has a negative slope. That should be pretty clear. The b and a are coming from the denominators of the original terms. And here's what to remember. The number under y squared, that b squared, that's associated with the numerator of the slope. And the number under x squared, it's a squared, that's associated with the denominator of the slope. This should make kind of sense because the slope of a line is change in y over change in x. So if we can remember that it's the letter under y divided by the letter under x, well, the square roots of those anyway, then should make it a little bit easier to remember those equations. In the case of a vertically oriented hyperbola, we've got y is equal to plus or minus a over b times x. And the reason it's switched a over b is because a squared is associated with the y squared, and so is still in the numerator. And b squared is associated with the x squared, so it's still in the denominator. Again, those square roots. So it's still the idea of the change in y over change in x. And always remember, the letter that's associated with y is in the numerator of the slope, and the letter that's associated with x is in the denominator of the slope. And because these equations have a squared and b squared, we're going to square root those numbers to get a and b. Now I know this is a lot, and we're going to go through a few examples, and then I'll wrap up and give you all of these equations again. So, sit tight for that. But I have just a little bit more to go over on this page before we get to those examples. First, let me clean some of this up. Much better. And let's talk about how we're actually going to draw the graphs of the hyperbolas. X squared over a squared. We're going to use that term to find a. From the center, we're going to go a units to the right and a units to the left. Then using b squared, we're going to find b, and from the center, we're going to go b units up and b units down. We're going to use those dimensions to draw what's referred to as a fundamental rectangle. Once we have that rectangle drawn, the diagonals of the rectangle are what's going to give us the asymptotes. We're going to use the rectangle and the asymptotes to actually draw the branches of the hyperbola. Same deal with the vertically oriented hyperbola. We're going to use the square root of a squared, so a, and from there we're going to go up and down, a units from the center, that is. We're going to use the square root of b squared, so b, and we're going to go left and right, b units from the center. We're going to use those dimensions to draw our fundamental rectangle. Once we've drawn our fundamental rectangle, we're going to draw the diagonals, which are going to be our asymptotes. And once we have all of that down, then we're going to draw the branches of the hyperbola. Okay, so the way we've written all this out, a is always going to be the distance between the center and a vertex, whether it's horizontally oriented or vertically oriented. And whatever orientation we have, b is going to give the other dimension of the fundamental rectangle. And then to find the distance to the focus, we're going to be using a squared plus b squared is equal to c squared. Finally, the equations of the asymptotes will be y equals plus or minus b over a times x in the case that we're horizontally oriented. And if we're vertically oriented, we're going to use y equals plus or minus a over b x. All of this is for hyperbolas with centers at the origin. If the centers aren't at the origin, our equations are just a little bit more interesting. We end up with things that look like x minus h the quantity squared over a squared minus y minus k the quantity squared over b squared is equal to 1. Or in the case of a vertically oriented hyperbola, y minus k the quantity squared over a squared minus x minus h the quantity squared over b squared is equal to 1. In these cases, the centers of the hyperbola are going to be hk, keeping in mind that h is going to be associated with the x-coordinate of the vertex, and so it's the letter that's with the x, or the number that's with the x variable, and k is going to be associated with the y-coordinate of the vertex, and so it's the number hanging out with y.